Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over the formal definition of a limit, otherwise known as the precise definition or the exact definition. As of now, we've talked about limits, saying that we're getting closer or approaching values in x as our function approaches other values. But what does approaching really mean? What does as we get closer really mean? So we're going to go over that in this formal definition. So it says the limit of f of x equals L as x approaches a. We know this from just our basic definition of a limit. And it says if for a real number epsilon greater than 0, there is a real number delta greater than 0 such that the absolute value of f of x minus L is less than that epsilon value whenever or when 0 is less than x minus a, which is less than delta. Now this is a little confusing just looking at the definition, so let's talk about it quickly. We know this, the limit of f of x as x approaches a equals L. But looking at f of x minus L, we're taking our function and subtracting that y value or that function value we got for our limit. So you can think of this almost as the change in y. So we're saying that the change in that y from f of x to L, that distance is always less than some value epsilon. And that's whenever 0, we had to put 0 in there because we don't want x minus a to ever be 0, because depending on our function, that could be some point that's undefined. We're approaching that a value, so we don't want to get right on that a value, so we say greater than 0. And again, x is approaching a, so you can think of this almost as that change in x. And that's going to be less than some value delta. But how exactly does all of this work? Let's understand it by visualizing it with a graph. I have some function pictured to the left, and what I'm going to be looking at is the limit of my function f of x. As x approaches, I'm going to define my a value to be 2, and we know that that limit is, well, you can see that y value is 3. So that's part of my definition, but let's fill in the rest that we know. Now we know L and we know a. So when I have the absolute value of f of x minus L, I'm going to have the absolute value of my function minus 3. That's going to be less than some epsilon. We don't really know what epsilon is. We'll talk about it in a second. And then for the next part, 0 is going to be less than x minus my a value of 2, which is less than delta. So we filled in all of our given information, our L and our a. So now let's talk about epsilon and delta. So if I said that my epsilon value was, let's do 2, we're saying that this f of x minus L is always going to be less than 2. So remember up above, I said this was like the change in y. And what we're saying is that the change in y is going to be less than 2, the absolute value of that change. So if we're looking at the point as x approaches 2, we're looking at that value, that L value of 3. So if here is where my L is, a change in 2, I could either go 2 up to get to 5, or I could go 2 down to get to a value of 1. So my epsilon represents moving from that L either up that value of the epsilon or down that value of the epsilon. And because epsilon is greater than all those values, but what we're trying to figure out now, if we're given an epsilon, we're trying to figure out this delta. So based on our epsilon that's equal to 2, we're trying to figure out that delta value that's associated with that change in x. So what I'm going to do, knowing that I can go up 2 or down 2 from L, I'm going to draw lines extending out to see where that intersects my function. So I'm intersecting at this point here when I go up 2, and I'm intersecting at this point here when I go down 2. So those 2 points I've just marked, or when epsilon is equal to 2, when f of x minus 3 is equal to 2. Now we're saying that we're always less than that. So we're looking at all of this, all of those values in there. So if those points are associated with that epsilon value of 2, I can use them to find my delta value because every point has an x, y coordinate. And if I know my y coordinates for those, well, if I draw lines straight down, they're going to give me an associated x value. So I'm either going to get 3 or I'm going to get 1. And that 1 and that 3 is going to be related to my delta in some way. But remember, they're my x values. So you can see that if I took my x value of 3 and subtracted 2, I would get 1 for delta. Or if I took my x value of 1 and subtracted 2, I would get -1. The absolute value of -1 is a positive 1. I would still get 1. So when I have an epsilon value equal to 2, then my delta value is going to equal 1. And if I was to look at that x value, or that a value as x approaches 2, you can see that I'm either 1 to the right or 1 to the left. That's a change in 1. And I can do the same exact thing for a different epsilon value. Let's move to an epsilon value of 1. If I looked at an epsilon value of now 1, well, remember, that's associated with that change in y. F of x minus L is less than epsilon. So if my L is at 3, going up an epsilon value of 1 would bring me to 4. So that max is this point here, and going down an epsilon value of 1 would get me to 2 in the y, and that's this point here. And again, if you wanted to double check by plugging in those y values, 2 minus 3 gives you -1. The absolute value of -1 is 1. And then 4 minus 3 does indeed give you 1. So that point is those outer limits. So let's find those x values associated with each of those I just marked. If I go down, I'm at about 2.5 when I'm using that y value of 4, and I'm at about 1.5 when I'm using that y value of 2. So 2.5 minus 2 is going to give me 0.5, or 1.5 minus 2 is going to give me a -0.5, taking that absolute value. Delta would then be 0.5 in this case. And you can see, if I'm looking at as x approaches 2, that change either way, that distance is 0.5. So relating this back to our definition, you can see that as our epsilon values were getting smaller, so were those delta values. So as x was approaching some value, some a, then our function was approaching some value L. So when we first talked about that epsilon being 2, we got a delta of 1. Then when we shorten that epsilon value of 1, we then got a delta of 1/2. If I was to make epsilon, let's say 1/2, then you would see that our delta would also get smaller. Let's look at this next graph on the right. We're saying that the limit of f of x, our function, as x approaches 1 is equal to 1. So we have an L value of 1 and an A value of 1. So I know that the absolute value of f of x minus L, so -1, is going to be less than epsilon whenever 0 is less than x minus 1, my A value, which is less than delta. Now in that first part we had a linear function, here we have a cubic function, but the same method still applies. Let's look at an epsilon value of 1. So we're saying that f of x minus 1 minus our L value of 1 is always less than 1. So if we're always less than 1 for that change, then 2 minus 1 gives us 1, so that's that outermost limit, and 0 minus 1 gives us a -1, that was that lower limit. So moving up an epsilon of 1 or down an epsilon of 1, I'm going to go to 2 in the y or 0 in the y. 2 in f of x or 0 for f of x. So I'm going to go over and mark those points on my graph. Finding the x values associated with those points, you can see the x value here was 0, and the x value here was about 1.25. So as opposed to that linear function, our delta value is now potentially two different options. We have a delta value, remember, x minus 1, 1.25 minus 1, that's a delta value of 0.25 or 1/4, or this 0 minus 1 is a negative 1, taking that absolute value, we have a delta value of 1. So in this case, we got two separate delta values, but remember, this needs to hold true whenever we have this. So if I attempted to go a delta value of 1 this way, I would be at 2. And if I drew my line up to my function, well, you can see that definitely is going to be an epsilon value that's greater than 1. So in this case, when we find two different potential delta values, we take that smaller delta value. So delta value would be 0.25 or 1/4 in this case. And you can see that 1/4 will still hold true for that epsilon value of 1. It will still hold true to the left. That's why we're taking that smaller value. If I wanted a delta value of 0.25 to the left, you can see that that still is within my range of my f of x minus L. That still falls within that range. Whereas when I attempted to go 1 using that larger delta value to the right, I fell outside of my range. That epsilon value was a lot bigger than a change of 1. And I know this is a lot to take in, so we're going to continue to practice this, but let's again go over the steps. First, we're going to fill in those A or L values that are given. Then, depending on the epsilon that's given to us, we're going to shift that much in the y from our limit L. Once we make those shifts, either up an epsilon value or down an epsilon value, we're going to find the associated x values and take the smaller value. If they're the same, we take that value. If one is smaller than the other, we use that smaller value. So let's continue on to our first example. So it says, using the given graph and the limit of f of x as x approaches 3 equals 5/2, 2.5, we're going to identify the appropriate delta value for each. So this is what we're given. We know that our A value is 3 and our L value is 5/2, which I've already filled in. 0 is less than x minus 3. There's our A, which is less than delta. Then f of x minus L is always less than 1. Well, 1 is our given epsilon value. So we're saying that epsilon is 1. So if we have some delta value, then our function minus L is always going to be less than 1 for that delta value. We got to find what delta value makes this true. So let's go over to our graph. Our epsilon is 1. So if we're at 5/2 for L, moving up 1 will bring us to 3.5. Moving down 1 would bring us to 1.5. And this might be easier if I zoom in. So you can see this is our L value. This is L minus some epsilon, and then up here was L plus some epsilon. So if I was to draw this over to try to find the associated x value, I first need to figure out where L plus that epsilon intersects my function, and then I'll see where L minus epsilon intersects my function. Now I'll be able to find those associated x values. One of those is 5, and the other one is 1. But remember, what was x approaching? X was approaching 3. So if x was approaching 3, what's that delta value? What's that change? I have 2 when I'm doing my L plus epsilon, and I have a change of 2 when I'm doing L minus epsilon. So that delta value is 2. So hopefully this is making a little bit more sense. Let's do one more example with this linear function. And remember, I'm given that same limit that when I'm at 2.5 or 5/2 for L, that's the limit of my function equals L as x approaches my A value of 3. So in this next one, our epsilon value is 1/2. So we have to find the delta value that holds true. If 0 is less than the absolute value of x minus 3, which is less than that delta value we're finding, then our function minus L, the absolute value of that, is always less than 1/2. So we have to find a delta value where our function minus L is always less than 1/2. So if I added 1/2 to L, I would go up to 3 in the y. If I subtracted 1/2, I would go down to 2. But you can see that that's a change of 1/2 from L. What's that x value associated with when I add that epsilon? That's going to be an x value of 4. And the x value when I subtract that epsilon is going to be associated with an x value of 2. Now, what's that delta value where my change in y is always less than 1/2? That's a delta value of 1 unit either way. So delta equals 1. So with delta equaling 1, if 0 is less than that absolute value of x minus 3, which is less than 1, then this is always true. If I try to do a different delta value, let's say 2, like we had up above, well, we know that's not true because if we went 2 to the right, you can see that this is bigger than a change of 1/2. It was a change of 1. So once we find our delta values, that other part of our if statement always holds true. Now in the next example, again, we're going to be working with a graph. I have a piecewise function, so I have two linear functions coming together. So we're going to be using the given graph and the limit of f of x as x approaches 1 equals 2. I'm going to fill that in right now on my graph so I can visualize that. The limit of f of x as x approaches 1, so as we go towards an x value of 1, there's our a, our limit is equal to 2. So there's our point in question, that limit. We're going to identify the appropriate delta value for each. So I need to find the delta value that will make this true. If 0 is less than the absolute value of x minus 1, which is less than delta, then the absolute value of f of x minus 2 is always less than 1. So there's my epsilon value. You can see I have a, L, and they give me an epsilon value of 1. So let's use it. F of x minus 2 is always less than L. So if I moved an epsilon value of 1 up, you can see that I would intersect here. And if I moved an epsilon value of 1 down, you can see I will intersect here. Well, let's find those associated x values. This is an x value of 0, and this one has an x value of, it looks like 1.5, or 3/2. So let's find that delta value. Well, from a to 0, that's a change of 1, and from a to 1.5, that's a change of 1/2, or 0.5. And remember from up above, which one do we want to be our delta value? We want our delta value to be that smaller one. So delta is 1/2. If I attempted to use that larger value, 1, think about moving a delta value of 1 to the right of a. That would bring me to 2. And if I was at 2, my function would be at 4. And you can see now that that change from 4 to my limit value L of 2 is no longer 1. It's now greater than 1. That's why we take that smaller value. So you can see that if indeed we took that smaller value and went 1/2 to the left, well, our function value still falls within that epsilon of 1. It falls between those bounds. So in the case of a, our delta value equals 1/2. So if 0 is less than the absolute value of x minus 1, which is less than 1/2, then that second half of that statement is always true. Now, using the same graph, we're going to look at for an epsilon value of 3. So let's go ahead and erase what I've done, leaving that same L and A. An epsilon value of 3, I'm going to move up 3 or down 3 from L. If I move up 3, let me zoom out a tad, I'm going all the way up to 5. 2 plus 3 gets me to 5. 5 minus 2, 3. Moving down 3, I'll be at -1. So moving down to -1 or up to 5. Those associated values in the x are going to be, here I have 2.5, and here I have a -2. And remember, I'm trying to find that delta value. So what's my change from A? What's my distances from A? Well, this distance from A to 2.5, 2.5 minus 1 gives me 1.5, whereas this change from 1 to -2 is a change of 3. And which one am I taking? I'm taking that smaller delta value because that will hold true even when I go to the left. If I went 1.5 to the left, you can see that I still fall within that range of either adding epsilon or subtracting epsilon. So for B, I use my value of delta to be 1.5. And using this value for delta, that second half of the statement always holds true. Now next, we're going to look at one more example, except now we don't have a graph, but this function is fairly easy to visualize, so maybe we'll graph it as we go along. We're letting f of x equal x cubed minus 1, and a is going to equal 0. We're going to find the limit of f of x as x approaches a, and then for each of the given epsilon values, we're going to find the associated value of delta such that 0 is less than the absolute value of x minus a, which is less than delta, whenever the absolute value of f of x minus L is less than that epsilon value. So right off the bat, I want to fill in my conditions and I want to rewrite my limit so that I can visualize it. So we have the limit of f of x as x approaches a, which they tell us our a value is 0, is going to equal some L. Well, look, f of x is a polynomial function, so in order to solve that limit, we can just plug 0 right on in. So plugging 0 in, we get that L is going to be a -1. Now I'll fill in those conditions. If 0 is less than the absolute value of x minus a, which is x minus 0, which is less than delta, then we have the absolute value of f of x minus L, which is -1. So we'll have minus that -1 is less than epsilon. And feel free to rewrite minus that -1 as adding 1. So let me go ahead and rewrite what we just talked about really quickly, and then I'm going to show you another method to use before we jump into the graphing method. So we knew that the limit of our function x cubed minus 1 as x approaches 0 is equal to that -1. That's how we got that 0 is less than the absolute value of x minus 0, which is less than delta. And we also have that our function f of x, but I'm going to fill that in. Our function f of x is x cubed minus 1. So x cubed minus 1 is our f of x, and we're going to subtract that limit L, which is -1, and that's less than that epsilon value. And our epsilon is going to change depending on whether we're working with part A or part B. Now I'm going to simplify each of those inequalities. So I'm going to have 0 is less than the absolute value of x, which is less than delta. And think about x cubed minus 1 minus a -1. That's going to leave me with x cubed is less than epsilon. Now here is the part that makes solving these fairly easy. If I can get what's inside of my epsilon to look similar to what's inside of my inequality for my delta value, then I'll just be able to solve for delta. Let's walk through that quickly with part A. In part A, my epsilon value is 1. So I know that the absolute value of x cubed is going to be less than 1. I want to see if I can get an x within that absolute value. That's just by taking the cube root of both sides of my inequality. So I'm going to get that after I take the cube root, the absolute value of x is always less than the cube root of 1. And the cube root of 1 is 1. And look at that. I have this same inequality. So I know for part A, my delta value is indeed 1. And let's try it again. For part B, our epsilon value is 8, so if I plug 8 in, again, I want this inequality to look similar to this so that I can solve for that delta, so I'm going to take the cube root. So I'll have the absolute value of x is less than the cube root of 8, and the cube root of 8 is 2. So now I have the absolute value of x is less than 2. Well, the absolute value of x is less than delta. That means delta is 2. So then for part B, my delta value is equal to 2. The only difference doing it this way, it's a little hard to visualize the concept of getting closer to those values. It's hard to envision approaching these values when we're just using these equations. So we're going to go through each of these again using that graphing method. That way we'll be able to visualize as delta gets smaller, epsilon is also getting smaller. Essentially, as we get closer to A, our function is going to get closer to L. We're just using epsilon and delta now to show that that change is getting smaller and we're getting closer. So let's jump right back on into part A using the graphing method now. That way, we're able to visualize. So let's think about the epsilon value of 1. When I'm approaching an A value of 0, my function is approaching -1. So for an A value of 0, my limit is at that -1. And I know my function is x cubed minus 1, which is a cubic function that has an intercept of -1. So it's going to look something like this. Now in part A, my given epsilon is 1. So I'm looking at moving up 1 or down 1 as that change. If I moved up 1, I need to find that associated x value, and if I moved down 1, I would need to also find that associated x value. So moving up 1 in the y or down 1 in the y, how do I find those x values? Well, remember, I know that f of x is equal to x cubed minus 1. And as x approaches 0, I'm at L. So if my L or my y value is currently -1, think about going up 1, that would bring me to a function value of 0, or going down 1 would bring me to a function value of -2. So I'm going to have that 0 equals x cubed minus 1, or I'm going to have that -2 equals x cubed minus 1. I need to find those associated x values with each. So when 0 equals x cubed minus 1, if I add 1 to the other side and take the cube root of that, then I'm going to get a value of x equals 1. So I know that this x value is 1. What is this x value when I'm at -2 in the y? Well, if I added 1, I would get -1 equals x cubed. Taking the cube root of that, that would be that x is equal to -1. So then you can see that I have an x value of -1. Then, what's that delta value? Well, if my A is 0, I have a distance of 1 to get to +1 and a distance of 1 to get to -1. So that delta value associated is 1. So when epsilon equals 1, delta is equal to 1. If 0 is less than the absolute value of x minus 0, which is less than 1, then the absolute value of f of x minus -1 is always less than 1. Just filling in those different parts for part A in example 3. So for part B, we're going to do an epsilon value of, this should read 8. So doing an epsilon value of 8, we're going to do the same steps we did in part A. And it might be helpful for us to redraw this graph so that it doesn't get too messy. So here I've redrawn my function. I know that the limit of f of x as x approaches A, which is 0, is equal to L, which is -1. Using an epsilon value of 8, I'm either going to go up 8 from -1 or down 8 from -1. Going up 8, that's going to be -1 plus 8, which brings me up to a +7. -1 minus 8 is going to bring me down to a -9. So those are my two function values, 7 and 9. So I need to find those associated x values and then see what my potential delta is. So when 7 equals my function of x cubed minus 1, I'll solve for x. And when negative 9 equals my function of x cubed minus 1, I'll solve for x. Adding 1 to the other side, I'll get that 8 equals x cubed, and the cube root of 8 gives me that x equals 2. So I know this x value here is 2. Now when I add 1 to the other side, I get a negative 8. So now I'm going to have that negative 8 equals x cubed. Taking the cube root of negative 8, x is going to give me a negative 2. So now I'm at negative 2 in the x over here. What's that delta value? Well, if I know that my a is 0, I have to add 2 to get to 2 or subtract 2 to get to 2. So that distance is 2, meaning that my delta is going to be 2. So if 0 is less than the absolute value of x minus 0, so the absolute value of x, which is less than 2, then the absolute value of f of x minus that negative 1, so f of x plus 1, is always less than 8. So hopefully with this worksheet, you learned how to manipulate your epsilon and delta values in order to understand this definition. Again, what this definition is doing is it's replacing words like approaching and getting closer. Those arbitrary words, it's replacing them with formal definitions. So as that epsilon value was getting smaller, you can see that our delta value was also getting smaller, showing those different approaches. Now, all of these examples, this formal definition is theory-based, but I recommend getting some extra practice problems in, doing some more on your own so that you can really grasp this concept before moving on. So feel free to go to your textbook and look up more practice problems or try to come up with problems on your own. If you can create problems for a friend, you're going to have a better understanding of this concept. So once you get that practice done, continue on to the next video. But until then, good luck with your online learning.